Okay, I think my camera is turned off, so let me turn that on. Okay, let me handle one more thing over here and we can get started. Okay, I think my camera is turned off. Turn that on. Okay, good. I think I'm ready. Make this full screen. Okay, welcome. This is lecture 23 of Digital Design and Computer Architecture. And we're going to continue covering memory in this lecture and the remaining, I think we have 3 more lectures left after this. And today we're going to delve into memory hierarchy and caches. And clearly this is a quite exciting topic in computing system design today. And we motivated the importance of it in the last lecture. And we discussed how most of the real estate of modern chips is dedicated to memory hierarchy, and increasingly memory hierarchy is going to be a bigger bottleneck. And we're going to talk more about that today. But we're going to start with the basics of building a memory hierarchy and talk about caches. And then let's see how far advanced we can get. We may continue talking about caches in the next lecture also. Okay, so these are the readings. I added one more reading. This is a book chapter that we had written with one of my PhD students a while back on memory systems. And it's very accessible, in my opinion, on the topics that we're going to cover on memory hierarchy and caches. So I'd recommend people to read it. It should be very easy reading, actually. And I'm going to show you examples from that reading. I'm going to reuse some figures for this lecture. But the other readings stay the same. We're going to talk about Maurice Wilkes' seminal paper on cache memories in this lecture. So recall, I'm going to use several slides to refresh your memory on what we talked about last time. We talked about memory organization, memory technologies, and we said that all memories look similar internally if you focus on the arrays, and they're built as hierarchy of arrays. And this is one example array that shows a bank, let's say. And you can see that it's 2-dimensional and you have rows and columns. I'm not going to go into the details of it again. You can watch the last lecture again if you want to refresh your memory on how these arrays operate and how the cells operate and how they actually work essentially. But many memory technologies are similar, and we talked about SRAM as one memory technology. This is compatible with logic fabrication. As a result, it's used as cache memory integrated with the compute units. We also talk, and you can see that the 2-dimensional array structure is over here also. And we talked about DRAM as another type of memory technology. And we said that this is not compatible with logic because of the capacitor. So fabrication technology is different. As a result, DRAM is almost always off chip compared to the processing units. And you need to go through off chip interconnects to access it. And as a result, a lot of the design decisions made in DRAM chips are dictated by the cost of the DRAM chip, as well as the cost of going off chip, the pin count, for example. And we said that you cannot provide the full address to a DRAM chip. You just provide the row address first and then the column address. And we also said that the data output is also smaller. You can get 8 bits, for example, or 4 bits or 16 bits in existing DRAM chips. Okay, we also discussed the trade-offs between DRAM and SRAM, and clearly DRAM is slower, SRAM is faster. So the speed is a big trade-off, and certainly density is a big trade-off. DRAM is higher density, as a result, lower cost, and SRAM is lower density, and as a result, higher cost. We're going to talk a lot more about this to build the memory hierarchy today. And this is going to be a fundamental thing that we're going to discuss, basically speed versus size trade-off. But there are other trade-offs also across the memory hierarchy. We also briefly mentioned phase change memory because this is going to be more important into the future. Today, we're in 2021. So we should really talk about this sort of technology, potentially gaining its space inside the memory hierarchy. And I'm not going to go through the details of it, but this is a non-volatile memory technology that can potentially replace parts of DRAM or augment parts of DRAM, and potentially replace also parts of SSDs or create another level in the memory hierarchy that we're going to discuss. And we also discussed the trade-offs between DRAM and PCM, and you can see that the list is longer over here because there are more differences that come into play, like endurance problems in phase change memory, which doesn't exist in DRAM, at least to a practical level that we know of today. Okay, so now with that, we also talked about the DRAM hierarchy. If you remember last lecture, we talked about how you can read a cache line from a hierarchical DRAM system, and I'm not going to go through that. Hopefully you remember that at this point. Now let's talk about the memory hierarchy and the reasons for it. And I think I showed you this picture earlier, but as you look at a system today, and this is not today, this is 15 years ago, you can see that a large fraction of the real estate, hardware real estate, is really dedicated to the memory hierarchy. So you see cores, L2 caches, L3 cache here, memory controllers, memory interface, and memory banks. And we're not even looking at, I'm not even depicting the regular L1 caches inside the cores over here. And there's a reason for it. We're going to talk today that L1 caches are tightly integrated with the cores, but that's part of the memory system also. Register files are also part of the memory system, as we will discuss today. And recall, I showed you this slide. This is one of the latest chips that we briefly discussed in earlier lectures. This is Apple M1. And you can see that a large fraction of the modern chips is dedicated to memory. You can see 12 megabyte caches here in the fast cores, high performance cores, 4 megabyte cache in the efficiency cores, as they call them, a system level cache. And GPUs also have things that are not designated over here. And you can see the memory channels are also part of the memory hierarchy. So if you extend this, you look at a chip like this. This is AMD Ryzen. It's one of the latest AMD cores, AMD chips, I should say. And you can see that the caches are growing bigger and bigger as well. This is what I show over here is really the fraction of the chip in green that is dedicated to L3 cache and L2 caches. You can see that's more than half over here. We're not even including the L1 caches over here. We're not even including the interconnect to go off chip. And also other parts that essentially enable access to outside world. So essentially, it's not an understatement when we say that way more than a half of a single chip, CPU chip, is today dedicated to memory hierarchy. In fact, that's increasing. If you look at the full system, like if you look at the entire hardware cost, clearly all of DRAM is dedicated to the memory hierarchy. So clearly most of your system design, all of your SSD is part of your memory hierarchy. So clearly more than 80%, 90% of your system is really dedicated to the memory hierarchy. And this is just the computing chip as we are looking at. This is another example. This is IBM's server chip, Power 10. IBM has a lot of server lines, Z series also. I didn't have time to get a good die picture of that. But you can see that IBM Power 10 is also quite heavily using memory on the chip. You can see that the L3 cache is 120 megabytes. L2 caches are 2 megabytes per core. And L1 caches are not even depicted over here because they're considered part of the core. And you can see that the rest is also, a significant fraction of the chip is for memory signaling and memory interface and other outside connectivity of the chip. So again, this is more than half clearly. And this is another example from NVIDIA Ampere. This is the GPU that we discussed, a 100 cores. And you can see that this also has a significant memory hierarchy. We're going to talk about this more because there are some differences over here. GPUs tend to be more compute. You can see that the compute intensity in GPUs is higher than the other chips. So there are a lot of compute units also in GPUs. So memory, at least in this particular picture, is not fully dominating yet, but it's increasing. You can see that the L2 caches are becoming bigger, etc. I'm not going to talk about this in detail at this point. Okay, but let's talk about, with that background, why is it happening? Basically, we want ideal memory overall because we want zero access time to get our data so that we don't stall the pipeline. We want infinite capacity so that we don't run out of space, so that the programmers don't go crazy. We're going to talk about that later on also. But having larger physical memory spaces is good so that you can fit more data in it. We want zero cost if possible, of course, and we want infinite bandwidth so that we can support multiple access in parallel. Remember, in GPUs, SIMD engines, you want high concurrency, many accesses per cycle if you have many load units that are loading things at the same time. And vector processors, SIMD processors, GPUs are great examples of this. So you want all of this at the same time. And clearly, this is very greedy, right? This is idealism. And unfortunately, we cannot get all at the same time, basically. The problem is ideal memory's requirements oppose each other. And let's take just two aspects of it. Bigger is essentially slower, and faster is more expensive. And this is very fundamental. higher bandwidth is also more expensive if you want to take a third aspect of it, basically. So bigger is slower because bigger, as you make the memory bigger, as we discussed last time, interconnects become longer, and it takes longer to determine the location. Even if you partition it to hierarchical arrays of arrays, the overhead of the interconnect still increases, basically. So bigger is slower, and there's no way to get around it, basically. Otherwise, it becomes magic, basically. Faster is more expensive. So you may have a memory technology that's faster than the other, but it turns out it requires more area usually. SRAM, for example, is a good example. SRAM versus DRAM versus SSD versus disk versus tape. And going from left to right, your cost reduces, but you also become slower, basically. So essentially, faster technologies are more expensive because they require more to build the bit cell that you're storing data in. And higher bandwidth is more expensive, as we discussed earlier. If you want to get higher concurrency, higher memory accesses per cycle, you need more banks, more ports, more channels, or higher frequency, or some faster technology that can provide more bits per cycle, right? And as a result, that is all that increases cost as well. So higher bandwidth, again, if you want to get bandwidth, it costs you. Okay, so faster can be obtained with other architectural techniques as well, which we're not going to talk about, but that also makes things more expensive because that increases the cost of memory access in terms of cost per bit. Okay, so if you want to visualize the problem with today's technologies, this may not be the easiest to read, but you can see that bigger is slower. You go from smaller SRAMs to DRAM, let's say phase change memory, flash memory, hard disk. You go from sub-nanoseconds to tens of nanoseconds and to hundreds of nanoseconds to microseconds to milliseconds, basically. And if you look at the, so bigger is slower, basically, as you go bigger. And faster is more expensive. You can see this is actually real data from 2021. And you can see that the SRAM is quite costly per megabyte, $0.3, whereas hard disk is $0.00003 per megabyte. So you can see the cost differential over here as well. And other memory technologies that are not depicted over here have their place as well. And this may be an easier to read version of that problem. This basically shows the problem in a table view, going from faster technologies, SRAM, all the way to hard disk. And latencies, you can see the latencies, you can see the capacity and latencies, and you can see the cost per megabyte. And today we're actually at a very interesting place that the cost per megabyte of memory is very, very low. That's why we can actually put flash memories everywhere today. If you can see it, flash memories cost us not that far from hard disk cost today. And that has enabled a lot of revolution, in my opinion, in mobile systems, for example, that cannot afford hard disks, but they can afford flash memories, solid state memories. And phase change memory is actually also getting there. As you can see, it's cheaper than DRAM today, but it's not as cheap as flash memory, but going forward, it's going to become cheaper. So it's always instructive to look at these numbers. So these are 2021 numbers, and the values also scale with time. If you were looking at these numbers in 2031, due to the scaling, technology scaling, these numbers will actually reduce in terms of cost, but the latencies are not reducing as much. It's very interesting to think that, because latency is a lot harder to reduce than cost. Cost is really packing bits in a given millimeter square, right? And that's easier to do as long as you can reduce the size of the memory cells, which is essentially technology scaling or Moore's law. You can basically put more devices in a given area due to technology scaling. But latency is a very different beast. So it's very harder to improve because you're dominated by the interconnect. And interconnects, essentially the length of the interconnect and the speed of the interconnect does not really scale well with Moore's law or packing more bits in a millimeter square. You need some other technology to scale the latency. That's why the latencies are not scaling. And to look at it in an instructive fashion, this is actually a slide that I used to use, which it has the data from 2011. So these are data that are 10 years old. And you can see that the cost per megabyte is much higher at that time. 10 years ago, SRAM is $10 per megabyte, whereas today we're at $0.3 per megabyte. Hard disk was $1 per gigabyte, whereas today we're actually much lower per gigabyte. This is per megabyte, but you can do the conversion over here. So basically, and we have also flash and PCM over here. So basically, a memory hierarchy, memory cost is becoming much better, but latencies are not becoming much better. And memory hierarchies are actually built to enable a trade-off between latency, cost, and also other things like bandwidth. Okay, so let's just take the latency and cost or capacity. Cost is always equal to capacity as well, because you're really fitting more bits per millimeter square, right? So let's just take those two aspects. And these two aspects motivate the memory hierarchy. Ideally, we want both fast memories and large memories, right? So that we can store a lot of data and have quick access to it. But unfortunately, we cannot achieve both with a single level of memory. Otherwise, it'll be magic. And the idea of a memory hierarchy is very simple, basically. Have multiple levels of storage or memory. They get progressively bigger and slower as the levels become farther away from the processor or the compute units. And you manage this hierarchy, these levels, such that you ensure most of the data the processor needs is kept at the faster levels. So whenever the processor needs data, ideally you will get the data from the fast level, and you don't need to access the slow levels. But the slow levels are there so that you can actually have access to large amounts of data. But whenever you're accessing the data, hopefully you get it from the fast levels. That's the idea of a memory hierarchy, basically. You get the best of both worlds, best of low latency memory as well as very high capacity memory. Then the question is, of course, how do you achieve this, basically? Clearly, having multiple levels of storage is easy, but how do you ensure most of the data the processor needs is kept in the faster levels? And that requires a lot of interesting innovations and ideas and algorithms to build caching mechanisms, prefetching mechanisms, and other memory hierarchy management mechanisms that we're going to talk about and introduce in this lecture and the next. But clearly, there's a lot of research that has been done in this area for more than 50 years, and we're not going to be able to cover all ideas. But this is essentially what the memory hierarchy looks like. And this is from the reading that I assigned to you today. But basically, you can think of it this way. You have main memory that's large and slow, and you have some caches that are small and fast. And ideally, you don't access main memory. You access caches as much as possible, basically. If you have good management mechanisms, the data that you need goes into the caches before you need it. Okay, but we will see that that ideal is not always possible. So sometimes we access main memory, and when we access main memory, all of the pain of performance comes in because that really stalls the processors. Okay, so this is another view of the memory hierarchy. Basically, you want fast and small memories over here, and you have another level, let's say large but slow memory over here. You move what you use or what you need to the fast and small memory, and you back up what you don't need in the large but slow memory. And you can see that the fast memory is faster per byte over here, and as you go down the hierarchy, you get cheaper per byte. So with good locality of reference, which we will talk about locality, and with good management, your memory appears as fast as this fast and small memory, but as large as this large but slow memory. So you get the best characteristics of each. You get fast and large, and hopefully you don't get the small and slow, but you will get the small and slow if you don't manage the memory hierarchy well. Okay, and of course the idea is extendable, so you can certainly add a next level that's slightly slower but larger, and the next level that's even slower and even larger, but smaller than this latest level at the bottom. Okay, this is another view of the memory hierarchy. I think I've hammered it home, but the fundamental trade-off is fast memory is slow, large memory is slow, and we build a memory hierarchy. And you can think of register files as part of that memory hierarchy also, and they are actually, except they're managed by the compiler or the programmer. You put data from the cache into the registers, and registers work as if you remember when we introduced the register file in lecture 10, we discussed that register file works because you have locality of reference in values that you manipulate. And you basically store the values that you're going to need very quickly into the register file. And you have a small register file, 32 elements or 16 elements. GPUs have larger, of course, but 32 elements is reasonable today. And the compiler or the programmer manages this one. Caches are usually automatically managed, and we're going to talk about that. And there are clearly many trade-offs. Latency, for example, increases as you go from left to right. Cost reduces as you go from left to right. So register files are very costly. That's why we have small of them. Size increases as you go from left to right, capacity. Bandwidth reduces as you go from left to right. You have very high bandwidth access to register files and then to caches, but your bandwidth to main memory is lower because you have to go off chip. You have to go through off chip interconnects, IO pins, and that's just fundamentally harder to make as high bandwidth as something on chip, right? On chip, you just add a wire, right? And wires are not as costly on chip compared to off chip. And as you go even more off chip, the hard disk bandwidth is even lower. So you can actually see how latency, cost, size, and bandwidth scale as you go from left to right in the memory hierarchy over here. And this is from your reading, basically. This is an example memory hierarchy with 3 levels, L1, L2, L3. We don't show the registers over here. And you can see some values over here that I'm not going to talk about. Okay, so why does this work, basically? If you actually design a memory hierarchy like this, and even if you don't manage it very carefully, there is this locality of reference that happens in programs that enables a fast memory. So if you actually take whatever you accessed from the slow memory and keep it in the fast memory for some time, it's likely that you're going to access it again. And this is because of the locality of reference. And this is because if you recently used a value, you're going to reuse it again. And programs exhibit this locality of reference. So even if you don't manage the memory extremely carefully, this memory hierarchy is helpful. Of course, maybe a complicated memory hierarchy is not very helpful if you don't manage it carefully, but a simple memory hierarchy actually is relatively helpful. And locality is actually a general property. It's really a property of potentially life, right? One's recent past is a very good predictor of his or her or their near future, actually. Temporal locality, for example, is the general concept of if you just did something, it's very likely that you will do the same thing again soon. It doesn't apply in all circumstances, but it applies in some circumstances. For example, since you're attending the lecture today, there's a good chance you will be here again and again regularly. And that's temporal locality. Spatial locality is essentially locality also happens in time and space. And spatial locality is a space version of the temporal locality. Basically, it says that if you did something, it's very likely that you will do something similar or related in space. And for example, I mean, if you were having a real lecture where people were actually sitting in a classroom, which we will hopefully get to next semester. Unfortunately, we're missing out on that, and that's not very ideal this semester. But and we're also missing out on some of the interaction because of that, unfortunately. But basically, the spatial locality principle always held when I was giving real lectures. Every time I find someone in the room, they're probably sitting close to the same people for whatever reason, right? Maybe they're friends, maybe they just like that particular location to sit in the classroom. Essentially, they're spatially correlated with each other. And this is the notion of spatial locality. And we're going to see that in the program's access patterns also. But these are, in my opinion, the more general principles that can be applied to different things in life also. And you will see that this lecture actually is like that as well. Okay, so memory locality in the case of memory references refers to the fact that a typical program has a lot of locality in its references. And basically, it's temporal and spatial locality. So I'm going to narrow down this temporal and spatial locality definitions to the memory system and programs in a little bit. And one of the reasons is typical programs are composed of loops, but that's not just the only reason. Loops tend to iterate, and they tend to access different data, as you have seen earlier. But temporal locality says that a program tends to reference the same memory location many times, and all within a small window of time. And this is why registers help, right? You basically allocate a value in a register and reuse it many times, right? Caches also help because of that, as we will see. Spatial locality says a program tends to reference nearby memory locations, nearby in the memory address space, within a window of time. So both of them have a notion of time, but certainly temporal is just about time. Spatial is about memory locations that are close by each other within a memory region, let's say. So temporal locality, you can guess why. You basically load a variable, you're adding it to some other variable, but you may also be adding it to some other variable, right? Basically, if you load variable A, you may be adding it to 20 different things, and as a result, A has very good temporal locality. Right? That makes sense. Spatial locality is also intuitive, basically. Why does a program reference nearby memory locations within a window of time? Well, most notably, we've seen actually these two things. Instruction memory references, right? Whenever we're fetching instructions, we're going sequentially in the memory address space. We're fetching the instruction at PC, program counter, and then program counter plus 4, and then program counter plus 8. So every time we're incrementing program counter by 4, which means that we're going sequentially in memory, which means that we have good spatial locality. We're accessing nearby memory locations as we go forward in the instruction stream. So this is broken only when we change the control flow, all right? But even when we change the control flow, if the if the target address of a branch is to a nearby memory location, then you still have spatial locality, basically. Okay, so that's an example of why spatial locality exists, because of instruction memory references. But we've also seen why spatial locality exists when we talked about SIMD processors and GPUs, right? We talked about references to arrays and vectors. And these are often streaming and strided. Remember the example where we talked about element-wise averaging of the arrays, or the addition of arrays, or matrix multiplication. Basically, what you're doing is you're streaming through rows and columns in that case. And the references to arrays and vectors are usually streaming or strided. You almost always reference the next location, which is the stride of 1. That's what streaming means, actually, in this particular case. Or you may have a stride of 2, 3, 4, 5, 10, a small stride. Basically, that enables you to have a spatial locality because now you're accessing something close by in memory to what you've accessed before. So clearly, many examples exist to support this. And that's why the memory hierarchy, as we described it, works, because it can exploit both of these types of localities, both temporal and spatial localities. And we're going to talk about that, basically, how to exploit both. Caches exploit both. If you want to exploit temporal locality, what you need to do is, whenever you bring some data elements from main memory, you put it into a fast memory, let's call it a cache, and you just keep it there, right? And if it has temporal locality, you will access from that fast memory. If you want to exploit spatial locality, whenever you need to access one element, let's say A, memory location A in memory, you access memory location A, you bring it into the cache or fast memory, but you don't only bring that. You bring some nearby data in nearby memory locations as well, in the anticipation that you will have some sort of spatial locality. And that's enabled. So you basically bring a bigger block of memory, bigger region of memory into your fast cache or fast storage. As a result, you can exploit spatial locality. And if the program needs address A+1, for example, you've already brought it into the cache when you brought address A. Okay, so for existing systems exploit both of these, and we will see that. Okay, so and I've already mentioned this, but I'm going to go through this again a little bit more formally. So caches exploit temporal locality, and the key idea is to store recently accessed data in automatically managed fast memory. And automatically managed fast memory is called a cache today. We're going to talk about manual management also. There are manually managed memories as well, and we're going to get back to that. But modern caches actually are automatically managed, and cache, the meaning of cache has been very strongly associated with this automatic management. If you manually manage a fast memory, it's usually called a scratchpad memory or another memory level, basically. So when you hear the word cache, you should really think automatic management today. Okay, so there's one question. Is this prediction for memory similar to branch prediction? Can you use some ideas from branch prediction here? Potentially, yes. So if you want to optimize, yes, potentially. Basically, if you want to decide what to cache and what not to cache, you can potentially keep some history, for example, and decide, oh, I didn't reuse this region before, so I'm not going to cache it. Certainly, yes. Certainly, you can have more advanced ideas to do the management more intelligently. Absolutely. So basically, you can do history-based management in caches. But I'm not even talking about that at this point. I'm talking about basically saying, whenever you access some data, bring it into this automatically managed fetch memory. You don't even do it intelligently. You do it every time. But of course, if you're not going to reuse the data, this may be a bad idea, and you can improve on this idea by adding prediction mechanisms that decide or that guess which data is going to be needed in the future and keep them inside this fast memory. And we're going to talk about that when we get more advanced, basically. Very good question. Okay, so this is the temporal locality aspect. Basically, anticipation is that same memory location will be accessed again soon by the program or by some other thread that's going to access the cache. So think about it as well. So it may be accessed by this thread or by some other thread or by some other program also potentially. So that's the temporal locality principle, basically. Recently accessed data will be accessed again in the near future. And if the data obeys this principle, then that's great. Caches work. And this is what Morris Wilks had in mind in the seminal paper that I assigned you as reading. That's 2 pages, by the way, only 1.5 pages actually. And he says over here, the use is discussed of a fast core memory of, say, 32,000 words, that's old times, as a slave to a slower core memory of, say, 1 million words, again, old times, in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. And this is a beautiful depiction of what a cache is, basically. Okay, so let's talk about spatial locality also. Spatial locality, the idea in exploiting spatial locality in a cache is we would like to store the data in addresses, memory addresses, adjacent to the recently accessed one in automatically managed fast memory, called a cache. So we don't just store the recently accessed location, but we also store the data in addresses that are adjacent to that location. So we store a block, let's say, this is called a cache block or cache line, as we will see. So to be able to do this, you need to logically divide memory into equal. There are many ways of doing this, but in hardware caches, you logically divide memory into equal size blocks because hardware management is easier if you have equal size blocks, and fetch to cache the access block in its entirety completely, as we will discuss. And the anticipation is that this nearby memory locations within the block will be accessed soon. Not just the recently accessed data word, but everything within the block. Okay, and this is the spatial locality principle, nearby data. And the anticipation is that nearby data in memory will be accessed in the near future. And we also discussed why this may happen in real programs. And this is what one of the earliest processors that implement the cache implemented, IBM 36085. IBM 360 is an architecture. It's a mainframe architecture that has been extremely successful. It's actually one of the oldest architectures. In fact, IBM 360 is the first system that really used an 8-bit byte, for example. The reason why we have byte, the notion of byte, is IBM 360 actually used it. They went from 6 bits to 8 bits, and it worked for the rest of the remaining, I guess, 50 plus years right now. But they also implement the cache, and they had a 16 kilobyte cache with 64 byte blocks. And there's a beautiful paper that talks about how this works. Amazingly, today, L1 caches are not so dissimilarly sized, basically. Block sizes are similar. Cache sizes are maybe a little bit larger, but 64 byte blocks are quite common today. And there's a reason for it. L1 caches are very tightly integrated with the processing core. So the requirements of an L1 cache are usually dictated by the processing core, as we will see. But L2, L3, L4, other caches can be much bigger, and they can have different size blocks also, as we will also see. But spatial locality principle is also what we discussed. Okay, so I have an analogy for this very quickly. Basically, if you're studying, you may have books, right? And your books actually may form a hierarchy as well. Maybe you can call it a book hierarchy, right? You may have a book in your hand. That's the thing that you're processing at this point. That's the data that you're processing at this point. So it has to be in your register file, which may be your hand. You may have some books on your desk, and maybe those are recently used books. They tend to stay on your desk. These are the books maybe for classes you're taking, maybe computer architecture books, and maybe things that you have recently used and that you anticipate to use. But of course, they stay on your desk until the desk gets full. Once the desk gets full, you may need to evict the book from the desk, which may look like a cache, right? And you evict the book and you you put it to the bookshelf. And in the bookshelf, you may organize your books some way. Once your bookshelf gets full, maybe you put some really unnecessary or not so used books to boxes at home. And you may also have boxes in storage, not at home, right? That store books that you really don't anticipate using, right? So this looks like a memory hierarchy to me. Basically, the data that you anticipate to use are actually closer to you, but whatever you have closer to you has limited space. Your hands clearly can hold, if you're lucky, maybe 3 books, right? But usually 1 book or so. Your desk, depending on the size of your desk, but it's usually small. It may not hold a lot of books. Your bookshelf may hold more books, and then boxes and storage can be essentially unlimited as long as you're willing to pay for it, right? But this is the temporal locality principle, right? Basically, recently used or frequently used things, you try to at least keep closer to you and not long latency access in storage, for example. But also there's a spatial locality aspect of it as well. So for example, you may actually organize your books based on some content in your bookshelf. And if you do that, physically adjacent books in the space may be needed around the same time. And this is exactly the spatial locality principle in caches that we have discussed earlier in programs. If you have organized your data nicely, you may actually need the books that are spatially correlated, that are closely located in your bookshelf at the same time. That also holds for your cache in your desk, for example. If you put things nicely, you may actually get things, you may actually need multiple books at the same time, and they happen to be in the same place, in the same region. But if you actually randomly distribute your books onto your bookshelf, you may actually have no spatial locality, right? Because you may need a book, a computer architecture book, let's say, and let's say you have 10 computer architecture books, and they're all randomly distributed in your bookshelf, and you have no spatial locality, essentially. So you have to access different locations. So you cannot exploit spatial locality. You can exploit spatial locality only if you co-locate your data that you're going to access together. And that's true for programs also. And we discussed this when we talk about GPUs, for example. If you really want to get good performance, you want good spatial locality in your GPUs, right? Okay, there's one more question. If some memory from the large slow memory is called, does it first go through all the smaller memories and then to the processor, or does it go there directly? So that's a very good question also. That depends on how you manage the memory hierarchy. Usually in a traditional system, it may go through, it may be actually put in all of the caches, but you may actually decide to bypass some of the caches also. So existing systems actually enable bypassing of the caches, and in hardware, there are a lot of proposals to actually do the management in an intelligent way. But those are all design choices in the memory hierarchy. That's why memory hierarchy is very rich in terms of design choices. Okay, so caching in a pipeline design. I mentioned this earlier, but the cache needs to be tightly integrated into the pipeline, actually. Ideally, you want access in one cycle so that load-dependent operations do not stall. So level 1 cache is very tightly integrated. So, but in a high-frequency pipeline, you cannot make the cache large, basically. But you want a large cache and a pipeline design at the same time. And this is one reason why you have a level 1 cache that's tightly integrated into the pipeline, and you have a cache hierarchy after that. Level 2 cache, level 3 cache, level 4 cache. In this case, we show only level 2. But keep this in mind. Level 1 caches are always very tightly integrated into the pipeline because the processor needs to supply data to the load as soon as possible. 1 cycle, maybe 2 cycles, maybe 3 cycles, maybe 4 cycles. But you don't want to extend that time much longer because the latency is not easy to tolerate. And we discussed a lot of latency tolerance mechanisms so far. So if it's 100 cycles, that's bad, basically. That's why we have a cache hierarchy today. And level 1 cache design decisions are mainly dictated by here. Level 2 cache design decisions are actually much more free, if you will. And level 3 cache is much more free, clearly, because they're not tightly integrated into the pipeline. Okay, let's talk about manual and automatic management. As I mentioned, this is going to be important. So who manages the data movement across these levels? You have a fast memory. Clearly, register files, we talked about programmer or compiler manages. Potentially, you can imagine systems where hardware manages it also, but then how do you actually reconcile the programming of registers and the hardware management? That's a different issue we're not going to talk about. But register files, we can take it for granted that programmer manages. But what about cache levels? Manual means programmer manages data movement across different levels. Automatic means hardware manages data movement across levels transparently to the programmer. And this is another great example of the programmer microarchitect trade-off. So manual makes it hard on the programmer, of course, right? Too painful for programmers on substantial programs, unfortunately. But it used to be the case, basically. In general purpose systems, you had core versus DRAM memory in the 1950s, all the way into 1970s. And essentially, the programmers managed multiple levels of memories. Today, there are actually some systems that have cache. I don't want to call them caches necessarily, but these are scratchpad memories that the programmer can manage. Programmer decides to put, they have full control on the memory structure, and they basically decide what to put into this fast memory structure. It's called scratchpad in general. And embedded processors have it because in embedded processors, programs are usually simple. Programmers know what they're doing, and they want to get predictable performance. So they usually avoid the caches. GPUs have scratchpad memories, as we briefly discussed. I'm going to show you some pictures. They're called shared memory, unfortunately, in the GPU terminology, and not a good terminology. It's better to call it scratchpad memory. Shared memory means something else. It's shared between different processors, for example. Unfortunately, some companies decided to call it shared memory, but bad idea. It's shared across different threads, sure, but it's really a scratchpad. That's what distinguishes it. So some machine learning accelerators also have scratchpad memories today, increasingly, because, again, programs are relatively simple. You can actually manage the memory hierarchy potentially better than what hardware could do. But GPUs also have caches today that are automatically managed. I'm going to show you examples of this. Automatic management, hardware manages the data moment, as we said, transparent to the programmer. So the big advantage is programmer's life is a lot easier. So with complicated programs, the programmer doesn't need to deal with it. And the average programmer doesn't need to know about caches. You don't need to know about how big the cache is, what its parameters are, how it works to write a correct program. But if you want a fast program, maybe you do need to know some of those properties, and you do need to arrange your data so that it fits into your caches, for example. And we're going to get back to that. We're going to talk about software management of caches later in this lecture. So correct program, no problem. You can write it and take advantage of the caches. But if you want the maximum performance, even in an automatically managed memory hierarchy, you still may want to optimize your program and data so that you can exploit the memory hierarchy much better. So let me give you some examples. So this is actually a GPU, a very recent GPU, NVIDIA Ampere, and they implement both caches and scratchpads at the same time, essentially. So L1 cache, for example, L1 level has 192 kilobytes of memory per streaming multiprocessor. It can be used as L1 cache and or scratchpad, depending on what the programmer chooses. And the programmer can choose this on a per kernel basis. So the programmer can decide whether hardware manages it or they manage it. That's nice, basically. There's an option. Nice in the sense that expert programmers can decide what they need to do, but the average programmers can also say, okay, I don't want to deal with it. Let it be managed in hardware as a cache, right? So that makes programmability easier, while also giving an interface to the expert programmers so that expert programmers can take advantage of this memory in the way they believe is the best way to take advantage of. But again, programmers may be wrong sometimes as well, right? So L2 cache, on the other end, is huge, as you can see, 40 megabytes, and that's automatically managed. That's why it's called a cache. Okay, this is Cerebrus's Wafer scale engine. We mentioned this many times, right? I mentioned it in the last lecture also. It has a huge amount of on-chip memory, SRAM memory. And it turns out that SRAM memory is used as a scratchpad memory. So basically, this is the whole Wafer scale engine. You can see that there are 84 dies, and each die has, a single die has 4,500 or some tiles. And each tile has a scratchpad memory and an accelerator block over here for machine learning. And that scratchpad memory is managed by the programmer or the compiler, essentially. And it's 48 kilobytes, as you can see. So you basically program this entire accelerator tile by tile and then communicate between tiles. But each tile has a scratchpad memory that's manually managed, as you can see, which is interesting. And the total amount of manually managed scratchpad memory is 18 gigabytes on the full chip. And there's no shared memory according to Cerebrus. And you can see that this number became much larger in the recent generation for 40 gigabytes. Okay, so that's the distinction between automatic versus manual management. And there are clear trade-offs associated with it, right? So let's talk about caches. So caches are actually automatically managed, and I'm going to assume that in this lecture and future lectures. Whenever we talk about manually managed, it's called scratchpad memory. And automatic management was what Maurice Wilks had in mind. I already read you the summary, and this is the paper. But basically, he says by slave memory is a cache memory in this particular case. I mean one which automatically accumulates to itself words that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of main memory access to be incurred again. So it's beautifully stated this way, basically, as you can see. And in this particular case, the cache that was proposed by Maurice Wilks, well, it was obviously automatically managed, but also it was also a temporal locality cache. It didn't exploit spatial locality, which is interesting. Okay, there's a historical aside. I'll go through this relatively quickly, but it turns out Maurice Wilks' paper is not the first paper on caches. There are earlier papers like these two. The first one is more of a larger virtual memory-based system that talks about automatic management of disks and other memories. But the second one is very interesting because it's a real hardware cache that was proposed in the design of some processors. And you can see we're going to look at pictures that kind of look like this, basically. They called it a leukocyte system. So this is main memory for them. You can see that there's an address register and data register. And this is a cache for them. Basically, this is the tag store, as we will see soon. And this is the data store. And you look up the tag store to, the processor looks up the tag store to figure out whether the data is in the cache or not. If it's not in the cache, then you go to the main memory. If it is in the cache, you get the data from the data storage. So we're going to take a look at that soon. But essentially, a cache looks like what it looks like in 1962 today, except the management algorithms may be very different. So a modern memory hierarchy looks like this. Basically, I'm not going to go through this in a lot of detail, but register files are part of the memory hierarchy, as I said. They're manually managed, compiler or programmer managed. And you do the spilling to the main memory. And the main memory, there's automatic hardware cache management in these levels. And there's clearly main memory that the programmer has exposure to. And then there's another automatic level of management for swap disk, which we will talk about in the virtual memory lectures. What if you run out of main memory, basically? Then you actually swap the data to a larger disk. And this is also automatically managed today. In the past, this used to be manually managed. And that was too painful for the programmers. As a result, virtual memory was invented and demand paging was invented. And as a result, this part is also automatically managed. But keep in mind that there's this part of the memory hierarchy as well, register files. And there's a swap disk, which we will talk about in the next lectures. But in this set of lectures, we're going to focus on the caches. Okay, before we take a break, let me quickly talk about hierarchical latency analysis, and then we're going to go deeper into the caches. So if you look at a memory system that looks like this, clearly it has many levels. And this is very much representative of an existing system. Maybe the numbers are different in different systems, clearly. But basically, you can do a hierarchical latency analysis. And this is also in your reading, so I'm going to go through it relatively quickly. But basically, a given memory hierarchy level, I, has a technology intrinsic access time, or latency. Let's call it small ti. But you have also a perceived access time, large ti, that's longer than small ti, because you may actually not find the data at a given memory hierarchy level I, right? Because it's caching. So basically, except for the outermost hierarchy, which is really the swap disk in this case, or main memory if you ignore the swap disk, there's a chance whenever you query a particular memory structure or cache structure, there's a chance you're going to hit, and there's a chance you're going to miss, right? So the probability that you're going to hit is called a hit rate. You hit in the cache, which means that you find the data in the cache, and the access time is called ti, small ti. That's the intrinsic access time. But if you miss, then that probability is called mi. And the access time now it becomes ti to figure out whether you hit or miss, small ti, plus the perceived access time of the outermost, the outer level, the next level in the hierarchy. So basically, you can do a hierarchical latency analysis with this equation, basically. If you hit, you get the ti latency. If you miss, you get the ti, small ti plus large ti plus 1 latency, which is the access latency of the outer structures. So if I go back over here, so if I hit in the L1 cache, I have a small ti latency, nanoseconds. But if I miss, then the latency that I see for all of those misses is the outer L2 caches, essentially large ti, which makes sense, hopefully. But of course, there are some invariants, which is hit rate plus miss rate at a given level should be equal to 1. You either hit or miss. That makes sense, hopefully. And you can determine the latency or the perceived access time of the level by multiplying the hit rate with the intrinsic access time of the level and adding to it the miss rate multiplied by the intrinsic access time of the level plus the perceived access time of the next level. In other words, you can actually simplify it by saying for hits or misses, it doesn't matter. You have to access the cache to figure out whether you hit or miss. That's what TI means, small TI means. Technology intrinsic TI means that at that level's access time. Plus, for misses, you pay the penalty of the next level's perceived access time. Make sense? So basically, you can basically put values into this hierarchical equation, which I'm going to do before I take a break to show you what it looks like, essentially. Okay, so I've already mentioned this basically. Hits, HI and MI at the level are defined to be hit rate and miss rate of just the references that missed at level I plus 1, I minus 1. So basically, these are the references that are seen by a given level, I. Okay, so this is the recursive latency equation then. The perceived access time of a level, I, is equal to the intrinsic access time of that level I plus the miss rate at that level I times the perceived access time of the next level in the hierarchy. So if I is 1, that's L1. This large Ti plus 1 is L2's perceived access time over here. Okay, so what do you want ideally? The goal, you want to achieve desired T1, level 1 latency within allowed cost. T1 is level 1, basically. That's the closest you can get because we're not talking about registers. Ideally, you want to minimize that and you have something desirable. So ideally, you want to make the perceived access latency very similar to the intrinsic access latency by minimizing the second part of the equation. But it's not always possible, clearly, right? How do you make it possible? You try to keep the miss rate from a given level low, or you try to give keep the perceived access latency of the next level low. And these are both things that you can optimize potentially in the program or in hardware. And we're going to see that. This is actually fascinating, I think. Fascinating to think about it more formally like this. So if you want to keep the miss rate of a level low, you can increase the capacity, right? That's obvious. It lowers MI, but it may increase your intrinsic access latency at that level. So increasing capacity may lower your miss rate. Not always, sometimes. In general, it does. But it also increases your intrinsic access latency. But you could also lower miss rate by smarter cache management that we briefly discussed based on a question from one of your colleagues, right? So you can basically be careful about what you place into the cache. You can be careful about what you replace from the cache. You can anticipate what you do need, what you don't need. And you can prefetch into the cache such that you minimize the misses whenever the processor needs it. Alternatively, or maybe together with keeping the miss rate low, you can try to keep the perceived access latency of the next level low. And how do you do that? You may make the lower hierarchies, or L2 caches, L3 caches, faster, but then your cost may increase. Because how do you keep it faster? You may increase your capacities, for example, or you may actually reduce the capacities depending on what you're trying to optimize exactly. So this may increase the cost. Or you can introduce intermediate hierarchies as a compromise, but that may also increase the cost. So basically, this is not an easy optimization problem, as you can see, because it may add a lot of levels. It also is very much workload dependent, program dependent. Okay, let me give you a quick example of this latency equation, and then we're going to take a break. But basically, let's put real values over here in this equation. And I'm going to use Pentium 4 as an example. And remember, we saw a picture of Pentium 4 in the past. This is the Prescott version, 90 nanometer version. And you can see that L1 data cache is 16 kilobytes, L2 cache is 1 megabyte. And ignore the 8-way. We're going to talk about associativity. There's an instruction cache called the trace cache, which we're also going to ignore. But Intel Pentium 4 is real, and it has a huge L2 cache. I think this is the 2 megabyte version. But again, this is circa 2004 or so, or 2005 maybe. But you can see that the L2 cache is occupying a lot of space over here. But these are the values in Pentium 4, at least one version of Pentium 4. Basically, the capacity of L1 cache is 16 kilobytes. Intrinsic access time is 4 cycles for integers. Ignore the floating point because floating point requires wider values, so they require longer cycles. L2 data cache capacity is 1 megabyte in this particular processor, and the access time is 18 cycles. Very interesting, right? Main memory, we're going to assume that the access time, intrinsic access time, is 50 nanoseconds or 180 cycles. And this is very optimistic, by the way. Usually, main memories are much longer. So notice that best case latency is not 1, it's 4. The intrinsic access time of L1 cache is 4, basically. Very interesting, right? And worst case access latencies can be up to 500 plus cycles, which we're going to talk about. But let's take a look at this equation. If M1 is equal to 0.1 and M2 is equal to 0.1, if you plug these values into the equation that I showed you over here, which I should have copied perhaps, what you get is T1 is equal to 7.6 and T2 is equal to 36. So how do you do this? Basically, you do this by looking at the outermost first. So for the outermost, larger T2 is equal to intrinsic access time of the L2 cache, 18, plus the miss rate from T2, 0.1, times 180, which is the perceived access time of main memory, which is equal to intrinsic access time of main memory because we don't have any other level. So basically, it's 18 plus 0.1 times 180, which is 18 plus 18, 36. So perceived access time of the second level is 36 cycles. And you put this value into the L1 cache equation, which is 4 cycles, T1, plus miss rate from L1, which is 0.1, times T2, right? And that actually gets you 4 plus 0.1 times 36, which is 7.6. So perceived access time at the L1 level is 7.6 cycles, which is a lot. And this is, your caches are actually working not so bad. Your miss rate from the first level is 10%. Only 10% of the accesses miss in the L1 cache. Only 10% of the accesses that go to the L2 cache miss in the L2 cache. Even then, you get 7.6 cycle latency in the L1 cache. That's a lot. Now let's take a look at something else. If your miss rate is 1% only in each level, now you get much closer to the intrinsic access latency of the level 1 cache, 4.2 cycles. That looks much better, right? But you need to get a 99% hit rate in the L1 cache and 99% hit rate in the L2 cache. May not be easy. Okay, now let's look at something else. This is your miss rate at the L1 cache is 5%, which is 95% hit rate. 95% of the references that you go into L1 cache hit. Now this goes to 5 quickly. So a small increase in miss rate in the L1 cache level leads to a very, very large increase, I would say, in the access latency, perceived access latency of level 1. Now let's take a look at this. Going from here to here, if you keep the same miss rate in L1 cache, 0.01, but increase the miss rate in the L2 cache by 50x to 0.5, we get 5.08, which is very similar to over here. So here, going from here, the second part over here to third part, we increase the miss rate in L1 cache by 5x. Here, going from second part to fourth part over here, we increase the miss rate in the L2 cache by 50x while keeping the other constant. And we get similar amount of latency, perceived access latency in the L1 cache. So this shows you that you can actually get similar latencies by managing the caches in different ways. And depends on how you get. So the second one may be more realistic, depending on your locality of reference. So miss rate in the L2 cache can be 50% because L2 cache actually sees references that do not get satisfied by the L1 cache, right? You access L1 cache first, and then if you miss, then you access L2 cache. So basically, you can see that the optimization problem is actually very interesting. You can get a similar access latency by either giving up a little bit on your L1 cache or giving up a lot on your L2 cache in terms of the miss rate. And that's why this optimization problem is actually not easy. And I will let you think about this a little bit. Okay, there's one question. So T3 is, large T3 is small T3 here because it's assumed that main memory never misses. Absolutely, yes. Here we're assuming main memory never misses. As I mentioned earlier, we don't assume there's a swap disk because that complicates the equations even more. But the real equation is, of course, more complicated. Okay, so this is a great place to take a break. So let's take a 10-minute break over here. And then we're going to talk about cache basics and operation. And then we're going to advance on cache basics and operation. So let's take a break until 15:23, and then we will continue this. Okay, I think it's time to start, but I will start with taking a couple of questions that were put over here during the break. So one, there's a question that says, if the caches use an exclusive policy, the miss probability of L2 would be lower though. No, not clear. So basically, there's clearly you can manage the caches in different ways. Exclusive policy means that data that's present in one cache is not present in other caches, right? We will talk about it later on when we talk about more advanced caches. So you have a choice as to where the data is in the hierarchy. A given block is in this hierarchy when you manage the caches, and you may actually have an inclusive policy or exclusive policy, and they have their advantages and disadvantages. But the hit rate, miss rate depends on the access patterns. But if you use an exclusive policy, yes, then you actually have more overall space because you're not redundantly using the space for the same block across different levels. But now you need to manage, you need to have management overhead in terms of your caches also in hardware. So it really depends. But that's a very good point, basically. You may have more space if you have an exclusive policy. And there's one more question, which is also interesting, but more research related. Basically, one of you asks that PCM can also be used as SSD, but it can also be used as memory. Could this mean that potentially one day there's no distinction between main memory and storage anymore? Absolutely, potentially, right? It's if you have a memory technology that's close enough, that's good enough as both memory and storage, and then you may actually use it both for main memory and storage. And there's a reason why these memory technologies are also called storage class memories. You can use them as both main memory and storage memory. And there's a lot of research actually going on how to enable both these technologies as both memory and storage. In fact, my group has written some papers on that topic also. There's a paper that we wrote for the workshop on energy efficient design in 2013 that essentially talks about a case for hardware software cooperative management of storage and memory that essentially says the same thing. We want to unify the management of storage and memory. But of course, today that's not done, and there's some challenges, system level challenges to enable it as well. So there's more to do to enable something like this. But technologies like phase change memory can be catalysts for those type of new ideas or old ideas maybe that have a new space in computing again. Then they can be catalysts that can enable more research as well as future products. But that's a very good point. That's beyond this course at this point, of course. Okay, now let's go back to what we were talking about. So now I'm going to more formally introduce a hardware cache. And we're going to talk about its basics and operation, and then we're going to build up onto management policies. And caching is a very broad idea, actually. Everything we discussed so far can be applied to software as well, because in software, you have a locality of reference, and you can actually build software data structures that act as your caches. In distributed systems, you can have software caches when you actually program across many machines in a data center. You may have local memory or far memory, or you may have actually local storage and far storage. And you can decide you build a software-based cache in your local storage or local memory, right? So all of these ideas that we have discussed so far are actually very broad reaching in systems in general. So we're going to focus more on the hardware caches soon. So before we focus on hardware caches, a cache is essentially any structure that memoizes frequently or recently used results or data. And this is very general. Again, it could be software, it could be hardware. And the goal is to avoid repeating the long latency operations required to reproduce or fetch. That should be fetched. I'm going to correct it. Fetch the results and data from scratch. For example, a web cache. In fact, whenever you're browsing, your browser may be caching the pages that you recently visited so that the next time you want to visit that same page, it loads directly from your main memory where it's cached that page at, as opposed to going over the network and fetching the page again, especially if the page is known to not change, so that this works, right? And sometimes the page changes and you get a different result in your cache versus when you force your browser to reload the page from the network. But essentially, this idea of a cache is used by many software constructs as well, applications as well, as you can see. And similar design decisions also appear in these caches, like the size, what should be the size of the cache, what should be put in there, what should not be put in there. You can also what kind of prefetching do you do into the cache? Can you preload? So for example, when you are visiting a web page, your browser may be aggressively prefetching the links on that web page based on some information. Like without any information, may actually be going and prefetching the links, right? And preloading them into this web cache. And if you actually click on that link, then the then the web page that you want to see is already in your local machine, basically, because it's prefetched. So clearly, this reduces the latency and increases the hit rate of your web cache. But this is one way you can prefetch, basically. Prefetch means preloading. And clearly, it works well with this sort of environment. But of course, if you're not going to reuse the data that the browser preloaded, then you waste some bandwidth to get that data. So you could have intelligent algorithms to decide that preloading, right? The browser can say, oh, I'm going to guess that the user is going to click on these links, so I'm going to prefetch them. I'm going to guess that this web page that the user has visited is not, they're not going to reuse it again, so I'm not going to cache it. So similar decisions exist, except software caches tend to be much more flexible in the sense that the block size, because you're not limited by what you can do in hardware or what you can do in hardware efficiently. Your block sizes can be variable. For example, you may decide to cache 8 bytes at a time, or 1 megabyte at a time, or maybe 1 gigabyte at a time, right? That's a lot, but you may decide that it's a good idea to do that caching. So you're not limited to a fixed block size, as we will see hardware will be limited to for efficient querying of the cache. So think about these when you think about caches. They're software. Clearly, the ideas that we're going to discuss are going to be applicable to many things in systems and software as well. But we're going to look at a particular case of a hardware cache. And most commonly in the processor design context, this is an automatically managed memory structure, and it's usually SRAM. For example, we want to memorize and fetch SRAM the most frequently or recently accessed DRAM memory locations to avoid repeatedly paying the penalty for the DRAM access latency, right? And even in this sentence, I don't quite tell you exactly what's cached, right? I say most frequently or most recently accessed. These are two different things, actually. How do you determine what's most frequently accessed? That becomes a question now, right? How do you determine what's most recently accessed? That's also a question, although that's easier question. So this is a conceptual picture of a cache from the reading that I assigned to you. Essentially, cache has a limited size of storage that can store some number of cache blocks. And cache block, essentially, you need two different types of information. One is the data in the block. It could be 64 bytes. I'm going to show you a toy cache soon that's not going to be 64 bytes. But in the most modern systems, you get 64 byte blocks. In some IBM systems, actually, the block sizes are much larger because they found out that for their server workloads, larger block sizes are a good idea, like 256 bytes. So you need to have storage of the data of the memory address associated with the data. And you need to have information about the cache block, like the address. That's called a tag in hardware caches, at least. So you need to have two different types of information, tag and data. Data is clearly the data at that address, of that block at that address. Tag is the address information and maybe some other metadata. For example, valid. Is this cache block is valid? Meaning, is there something in this location in the cache that I brought from memory? That's the purpose of a valid bit. It has to be in the tag store because you don't want to access the cache and get some random data that you didn't bring in, right? So you need to understand whether what you have in the cache is valid or not. You may actually have other bits, as we will discuss, like a dirty bit or modified bit. Is this cache block modified by the processor? That indicates that this cache block was modified. Maybe you need to write it back to memory when you're evicting the cache block. You may actually have some other bits that help you with the decision of whether which cache block you want to evict from the cache, if that decision becomes irrelevant in your cache at some point. What do you keep in the cache? What do you insert into the cache? You may actually have some more bits of metadata. So tag is essentially some metadata that describes the block. There has to be a valid bit. There has to be some portion of the address so that you can identify what this data is associated, what memory address this data is from. But there could be optionally dirty bits, like modified bit. There could be optionally replacement policy bits so that it can enable you to make a better eviction decision in terms of which cache block you should evict. And there could be even other bits that help you make a better decision in terms of prefetching or insertion, etc. So we will talk about those later. But this is the conceptual picture, basically. So if you look at a logical organization of a cache, there are many questions over here. But one key question is, how do you map the chunks of the main memory address space to the blocks in the cache? In other words, which location in cache can a given main memory chunk be placed in? So you can think of this conceptually as this picture over here. So you may have a physical address space of 8 gigabytes, for example, and you divide it into chunks. I'm going to call them blocks later on, but for this picture, entertain me with the word chunk over here. Essentially, these are chunks of 64 bytes. They're essentially cache blocks. But basically, you have a mapping problem. You have many of these chunks in the physical address space, but your cache may have only space for only 4 cache blocks. So how do you do the mapping, basically? Which cache block can a chunk be placed in potentially? And we're going to discuss this mapping. In hardware, you need to have a simple function to enable this mapping. You need to take the address, and some bits in the address specify which location can this chunk go to in the cache. And we're going to see different cache organizations that enable things. And they're going to differ in terms of the flexibility that they provide in terms of how many locations can a chunk be placed into the cache. So here, there are 4 potential locations in the cache, right? As you can see. A chunk can go to only 1 location, potentially. That's called a direct map cache. You don't have any flexibility. Now, different chunks can also go to the same location, and they conflict with each other, so you have a problem over there. But if a chunk can go to any location in the cache, this is called fully associative. So you have full flexibility. But now you have a different choice. Which location should you put it in? Okay, so this is a pictorial. We're going to build up to these, but direct map cache means that a given chunk in main memory can only be placed in one possible location in the cache, here, based on the address bits. It cannot be placed in any of the other three places in this small toy cache that I'm showing you. This is called direct mapped. Direct map means there's only one mapping location for a given chunk. There's also the opposite. This is clearly the most restrictive, right? There's also the opposite one, which is a chunk can be placed in any possible cache block in the cache. And we have 4, so this chunk can go to any of them. So this is clearly more freedom. And this reduces what we will call your conflict misses, but it makes your cache more complicated as well. So this is simple. This is more complicated. But here, because of the flexibility, you have more management possibility of your cache. Okay, and there's an in-between thing called set associative. A chunk can go more than one place, one potential cache block, but not to all possible cache blocks in the cache. So you have somewhere in between. And that's called set associative. And we will see that also. A chunk can go to a set of cache blocks, but not to the other sets. Okay, so we're going to see this by building the cache. But before we build the cache, let's talk about some more basics. So I'm going to define more. A block, now I'm going to define it a little bit more formally. This is really the unit of storage in the cache. This is also called a line. IBM terminology says line. Both are used actually in literature today, a cache block or cache line. I'm going to use block. Memory is logically divided into blocks that map to potential locations in the cache. So I'm going to rename that chunk to block, basically. So memory chunks are also called memory blocks, let's say. They map to potential locations in the cache. Okay, so on a reference, as we discussed, you get a hit or a miss on an access to the cache. Reference means access to the cache. If the address you're looking for, or if the block is in the cache, if the block you're looking for, because whenever you access the cache, you're basically looking for the block. You may be looking for something inside the block, but you access the cache using the block address, basically. So how many bytes in block doesn't matter initially, because the granularity of access to the cache is in terms of the block. So if the block is in the cache, you use the cache data instead of accessing memory. Great. If the block is not in the cache, you need to bring the block into the cache, and that's called a miss. So to be able to do that, you may have to evict some other block. This is called an eviction, meaning you replace something else in the cache. Okay. And whenever you evict something, you may have to write it back to memory also, because it may have been modified in the cache. The thing you're evicting, the block you're evicting, may have been modified in the cache because of a store instruction or write request into the cache. And as a result, it's dirty, and the memory doesn't have the updated value, depending on how you build your cache hierarchy. And as a result, you may have to write it back. So there's more complication now, right? Stores complicate the cache a little bit. Okay, there are important cache design decisions we're going to look at one by one. Not all of them, maybe. Well, actually, we're going to tackle all of them in some level of detail. We're going to look at placement a lot, for example. Placement says, where does a block map to in the cache? How do you place it there? And how do you find a block in the cache? This is basically how do you query the cache, right? How do you place the block? Replacement means what data do you remove to make room in the cache for an incoming block? Granularity of management says, what is your block size? Is it large or is it small? Can you actually do something like sub-blocking, which we will introduce? Now, this is going to be important because it determines how many blocks you can house in the cache, right? And we're going to see the trade-offs in terms of large blocks, small blocks. And in hardware caches, usually you have a fixed block size. Not fixed block size, a variable block size complicates the management significantly because now it becomes very difficult to address blocks, right? If you have, let's say, variable size blocks, 10 different sizes of blocks, how do you address these different blocks? That becomes a problem. In software, this is not a problem. In software, you can complicate things, but in hardware, it becomes very complicated to manage different size blocks. So we have a fixed size block. Write policy, we will discuss hopefully. What do you do about writes? Whenever you write to a block in the cache, what do? Do you write to the next level? Do you write to the next level? Do you also write to memory? Or do you just not write to any other level, just this cache, and then you propagate the updated value later on when the block is evicted? So there are a bunch of write policies, actually more than this as well. And then there's instructions versus data. Do we treat them separately? And in fact, instructions versus data, there's a reason why the first level caches, L1 caches, are separate. L1 instruction, L1 data, because they're tightly integrated into different parts of the pipeline, right? L1 instruction caches are needed in the fetch stage. L1 data caches are needed in the load access or store access stage. So they're different. But in the next level, L2 caches, do you have L2 instruction, L2 data separately? Because they have different access patterns potentially, right? Instructions may have more spatial locality than data depending on your access patterns. So these are very interesting questions. There are also other questions in terms of hierarchy management, like where do you place the data in the cache hierarchy? I think this was alluded to earlier. Do you place it only in L1 and then move it into L2 only when it's evicted from L1? Or do you place it into all memory hierarchy levels or some memory hierarchy levels, depending on what you anticipate is going to be used, depending on the locality characteristics of the data? So these are interesting questions, clearly. We're not going to tackle all of them, but we're going to try to tackle as much interesting things as possible. Actually, clearly, caching is a very interesting subject that has fascinated many people in the world, both software and hardware. In computer architecture, there are still cache papers being written. The earliest cache papers I showed you was from 1962. That's the earliest I could find. But today, we're in 2021, and people are still writing cache management papers, and people are still improving the cache designs in real processors. In fact, there's a funny thing, the main computer architecture conference where many flagship ideas were presented, one of the main conferences, International Symposium on Computer Architecture. Sometimes people make fun of it, saying that it's the International Symposium on Cache Architecture. Now, that's not true, of course, but there was some point where a large fraction of the papers that were published in this flagship conference were about cache management. Why? Well, it's so important. It's most of your chip, basically, most of your system, actually. How do you manage this huge data storage becomes very important for your performance, efficiency, reliability, and everything, essentially. That's why it's so important. Okay, now let me go into a little bit more hardware. So cache abstraction, this is still abstraction, but a hardware cache is indexed using an address, or searched, or queried, I should say. And as I said, a cache has two distinct components, tag store and data store. And tag store houses the metadata about the data that's in the data store. Essentially, you have a tag associated with each data block. So as I showed you over here, let's go back over here, this picture. Each cache block has a data portion and a tag portion. We're going to decouple these structures in hardware. Tag portions of a cache block will be part of the tag store. Data portions of the cache blocks will be part of the data store. So in hardware, we decouple them because we want to access them in different ways potentially, right? As we will see for later level caches. So they serve different purposes. You query the tag store, ask the question, is the address in the cache? And the tag store can give you a hit or miss, yes or no, basically. And if the answer is yes, while you're indexing the tag store, you may actually be indexing the data store, and the data store gives you the data associated with the tag metadata. Okay, so data store just stores memory blocks. Now, there are also interesting questions that we will discuss. Do you need to access them concurrently? At L1 caches, usually yes, but maybe at L3 caches, you may access them serially, right? Okay, we're going to talk about that as well. But at this point, the abstraction is that tag store is the metadata that gives you the hit or miss signal, and data store gives you the data itself. Okay, and we discussed you can calculate the cache hit rate. It's really number of hits divided by number of accesses to this level. And average memory access time, we kind of calculated earlier. It's the hit rate times hit latency plus miss rate times miss latency. So these are some metrics that you may be interested in that we may cover at some point. But there's an important aside that we're going to cover also, which I should let you know at this point, because it's important. The question is reducing average memory access time always beneficial for performance? And this may be something you may want to think about. And the answer is basically no. Reducing average memory access time is good. But as I mentioned in earlier lectures, this is ignoring something important, which is concurrency in the system. So you may have a memory access, and that its latency, average memory access latency is some, let's say 100 cycles after all of these equations. And reducing that latency at the expense of reducing parallelism may not be a good idea. Meaning that latency may be overlapped by some other operations that are going on in the memory system. And if you actually reduce the latency but destroy the parallelism in the operations, you may actually have worse performance. So this is just to again tell you that latency is not the only factor that goes into performance, right? Remember the performance equation? It's about execution time. It's not about latency in the end. And execution time is not affected just by average memory access time. It's also affected by how much of that latency actually gets exposed to the instructions, how much of that impacts actually the CPI, cycles per instruction. Right? So keep in mind that reducing latency is not always good for performance. It may be bad sometimes, depending on how it changes things. Okay, now let's talk about a basic hardware cache design. So we will start with a basic design. Then we will examine a multitude of ideas to make it better. And there are many ideas, as I said, so we'll be selective. So we're going to look at main memory. It's going to be logically divided into fixed size chunks. I'll call them blocks also from now on. But cache can house only a limited number of blocks. This is true for any level of the cache. Main memory, for example, here at 8 gigabytes, each block is 64 bytes. So if you look at main memory, 8 gigabytes is 2 to the 33, right? A block is 2 to the 6 bytes. So you have 2 to the 27 blocks in main memory. In your cache, you have only space for 4. So the question is, how do you actually do the addressing and where do they get mapped? So basically, each block address maps to a potential location in the cache determined by the index bits in the address. So we're going to use part of the address to index into the cache. And this is used to index into the tag and data stores. I'm going to show it pictorially. And this is going to be an example that I'm going to show you. But this is an example. We have a toy 8-bit address. It's not the memory that I showed you earlier. This is a memory address, but it's a small memory in this case. If it's byte addressable, you can calculate the size of the memory. It's 256 bytes, basically. And index bits may be these 3 bits that come from the middle. And by just looking at what I showed you over here, you can guess that a block is 8 bytes in this particular cache. I'm going to more formally show it in the next slide. But we're going to look at a toy example, basically. And then the tag bits are the remaining bits. So we're going to index the cache and get the tag from there, and then check if the tag matches the tag of the address, block address that we are looking for. Okay, so basically I explained you the cache access. More formally, let's take a look at what it means. So a cache access, you first index into the tag and data stores. These are memories with index bits in the address. You get the from the tag store, you get 2 things, valid bit and the tag. You check the valid bit in the tag store. If it's not valid, then it's a cache miss because the cache doesn't store anything in that particular location. If it is valid, then you check the tags, meaning you compare the tag bits in the address with the stored tag in the tag store. I'm going to show you this pictorially in a little bit also. And if they match, if the valid bit is set and the tag bits that's stored in the index matches the tag bits of the address that you're looking for, then there's a hit. Then you declare that there's a cache hit. That means block is in the cache. And that's it, basically. Then you can get the data from the data store. Basically, if a block is in the cache, the stored tag should be valid and match the tag of the block, which means that somebody should have, earlier, the processor should have brought the block into the cache, set the valid bits, set the tag bits in that appropriate index. Okay, so hopefully this makes sense. Now let's go into an example. So we will examine a direct map cache first, as I said, and then we're going to build into fully associative and set associative. Well, over time, we're going to build into fully associative. But direct map cache means a given main memory block can be placed in only one possible location in the cache, just like I showed you earlier. Now we're going to look at a toy example that could fit in one slide, basically.
So a toy example will have 256 byte memory, 64 byte cache, and 8 byte blocks. This means that if you have a 64 byte cache and your block size is 8 bytes, you can only store 8 blocks in your cache, right? You have 256 byte memory, which is not big, and 8 byte blocks. That means that you have 32 possible blocks in memory. So you have 32 blocks in memory. Your cache has space for only 8. Then you need to have a mapping function, basically. Okay, let's talk about this placement and access in the direct map cache. So I repeated what I said over here. We have byte addressable main memory, 256 bytes, 8 byte blocks. So memory has 32 blocks. And this is the main memory. This is your entire main memory. Assuming that the width of each block is 8 bytes. These are the block addresses. So each address of a byte is, so you have 8-bit addresses, as I showed you earlier, because you have 256 bytes and memory is byte addressable. But the block address is only 5 bits because you have only 32 blocks, right? We said that block size 8 bytes. So what we really care about here when we're indexing and comparing the tags in the cache is the block address, that 5-bit address, even though I'm going to show you the 8-bit address in full in a little bit. But basically, this is your entire main memory, and I've basically annotated the addresses. This is block address. This is block address 0, block address 1. This happens to be block address 8 over here, block address 16, block address 24, ... Okay, so we are going to assume a cache that can house 64 bytes, and it's 8 blocks. Clearly 8 byte block, so it has 8 blocks. So a direct map cache says a block can go to only one location. So this is our tag store and data store, beautifully again. This is the valid bit that I showed you. This is the tag, and this is data store. So how do we query the cache? So this is the valid and tag I showed you. So this is our 8-bit address. So the processor issues an 8-bit address. It's looking for this address. So it has the least significant bits are specify the byte in block. They're 8 bytes. The next least significant bits are 3-bit index. Why 3 bits? Because you have 8 possible indexes into the cache. And then the tag is the remaining bits, 2 bits over here. B is bits here. So what do we do to query the cache? We basically use the index bits to index into the tag store and the data store concurrently. Okay, so if the address is if you're looking for example, block 00000, index bits are 000 over here. So the querying gives us this location 000 over here. It gives us a valid bit and a tag bits, and the data store gives us data. Now, what do? We compare the tags bits and we check if the valid bit is valid. If valid bit is not valid, then it's a miss for sure. If the valid bit is valid and tags match, then you get a hit. Only in that case you get a hit in the cache, which means that somebody brought this block into the cache, set the valid bit and set the tag bits, and that's the block you're looking for. If you get a hit, then you get the data, and then you can multiplex out the byte in block from the 8 bytes. If you're looking for only 1 byte, for example, you can pick the byte you're looking for from those 8 bytes. Okay, so that's the simple indexing basically. So if you get a miss, then what do? You bring the block 8 bytes from the cache. What do? Basically, you set the valid bit to 1. You set the tag bits to 000, 00 if it's block 0, and you write the data into the data store. That's how you update the cache, and you could keep updating the cache whenever you get a miss, basically. Okay, so clearly this is easy to build in a hardware because you have simple indexing. This is a random access memory, right? Both tag store and data store, and then you have a comparator that compares the tag, simple content addressable memory, but just one place you compare, right? So the downside of direct map cache is blocks with the same index contend for the same cache location. So and they cause conflict misses when accessed consecutively. So let's take a look at this example. So if there's a reason why I colored blocks that are green over here. Block 0, block 8, block 16, block 24. They all happen to have the same index bits, 000. And they all map to the index 000 and the tag store and the data store, which means that only one of them can be in the cache at a given time, because there's no other way you can place any of these blocks into the cache because of the mapping function that I showed you over here, right? Which means that now if your processor access pattern is not good from the perspective of this direct map cache, if you access, so if you, let's take the good case. If you always access block 0 once, block 0 again, 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 except for the first time, you get cache hits, right? That's great. And then at some point you access block 8, you put block 8 into the cache, the first time you get a cache miss and you keep accessing block 8 again many times, you get cache hits on block 8. Now, what happens if you interleave accesses to block 0 and block 8? If your access pattern is like block 0 and then block 8, block 0, block 8, block 0, block 8, block 0, block 8, block 0, block 8. Now, this is a bad access pattern for a direct map cache because those two blocks conflict at the same location in the cache, index 0, 0, 0. You have to evict one block to make space for the other. And if you're doing simple management, whenever you're getting a block, you're replacing the or evicting the already existing block, you get a 0% hit rate. That doesn't sound good. And that's the problem with direct map caches, basically. Multiple blocks in memory map to the same location or same block in the cache. And there's no other place you can place those blocks. As a result, if you have a bad access pattern like this, you get a 0% hit rate. Okay, so let me more formally define. So in the direct map cache, two blocks in memory that map to the same index in the cache cannot be present in the cache at the same time. Direct map means one index has one entry, or one index can go to one possible location in the cache, essentially. If different blocks have the same index bits, too bad. And this can lead to a 0% hit rate if more than one block is accessed in an interleaved manner mapped to the same index. So assume that, I've already given you this example. Assume address A and B have the same index bits, but different tag bits. This access pattern, AB, conflict in the cache index, and all access are conflict misses, basically, except for the first two, which are things that you bring into the cache, right? Everything else is conflict because they conflict in the cache, even though you may be accessing only those blocks, block 0 and block 8, and none of the other parts of the cache are used, you get 0% hit rate because even though other parts of the cache, other blocks in the cache, or other indices in the cache cannot be used, you cannot place index 0, 0, 0 there because of the mapping function, as I said. So this sounds bad. Of course, you can imagine, okay, maybe I'm not going to replace the previous block in the cache, so I'm going to get a 50% hit rate. Yes, you may have smarter policies, but this is still not good. Okay, so the set associativity is built so that you actually avoid such conflict misses. So the problem was addresses n and n plus 8 in our toy memory always conflict in the direct map cache, right? How do we avoid those conflicts? So what we had was we had a mapping function. We had a mapping function of column of 8, and one index can go to only one location. Why not enable one index to go to two possible locations? So in other words, if you think hardware, instead of having one column of 8 possible blocks, have two columns of 4 possible blocks. So now I'm going to make my tag store looks like this, and data store also look like this. So I'm going to make my index bit smaller. So I'm going to still index into the cache, but I'm now going to have 4 possible indices, and each possible index, I'm going to have space for 2 possible blocks. Okay. Now, if I have to accommodate both block 0 and block 8, block 0 can go here, block 8 can go here. And the data for the block 0 can go here, and block 8 can go here. And I'm happy because both of them are in the cache. I don't get conflict misses. Now, what I've done is essentially, let me go back over here. This was the cache we started with. One column of 8 blocks, very rigid mapping. I've made the mapping a little bit more flexible. 2 columns of 8, 2 columns of 4, same number of blocks still. But one index can house 2 possible blocks. Now, if you have a bad access pattern like n and n plus 8, n plus 8, n plus 8 consecutively, you can accommodate both block n and n plus 8 over here, right? Okay, so how do you do that? Basically, you index into the cache. You get the valid bit and tag from both of these. These are called ways, by the way, ways of a cache. This is way 0, way 1. And an index is called a set now. It houses a set of blocks as opposed to a single block. And you basically need to check the valid bit and tag of both. And hopefully one of them only match, right? Assuming if there's any that match. So there's some logic that determines hit. And if you get a hit, you select which of the data. So this way 0 in the tag corresponds to this way 0 in data. This way 1 in the tag store corresponds to way 1 in the data store. So this logic basically says if I have a hit in way 0 over here, I should select the data coming from way 0 over here. And then you can decide which byte to get out of those 8 bytes, right? So now your index bits became smaller, your tag bits became larger, right? Because that's what we did, right? Okay. Okay, so there's one question basically. Wouldn't now n and n plus 4 contend for one of the two slots? Absolutely, yes. That's true because your index bits are smaller. But n and n plus 8 also contend for those slots. So there's more contention, yes. But if your access pattern is n and n plus 8, you solve the problem. But now, yes, n and n plus 4 also contend for those slots, yes. So certainly contention patterns change once your indices, once your index bits or mapping function changes, right? Indexing is really a mapping function, basically. Okay, so now you can take this to the next level. This is called associative memory within the set. So if you look at the set, way 0 and way 1, you're accessing them concurrently, and you're doing the content addressable match. You're basically checking the content of the tags, right? And you determine a hit or miss based on the content match over here, tag match. So there's an associative memory that we're including. Clearly, this is increasing the complexity of the cache. So there's a trade-off. But it accommodates conflict better, so you get fewer conflict misses in this type of cache. But then you get more complex, slower access, and a larger tag store also. Why is it larger tag store? Because now your tag size has increased. So there are disadvantages to this associative as well. As you can see, latency can increase in this particular case. But now you can have the same question, basically. Addresses 0, 8, 16. If you keep repeating them, well, unfortunately, you have only 2 places in the cache. You're back to square one, kind of. You get 0% miss rate if you mismanage your cache again. If you have a bad access pattern where you have 3 blocks that you repeatedly accessing in an interleaved manner, and they happen to map to the same set. This is called a two-way associative cache. Basically, two-way because in each index, you have 2 possible locations, way 0 and way 1, essentially. So you may run into conflict misses, again, in this case, by increasing the number of blocks that you're accessing in an interleaved manner. How do you solve it? You make the associativity higher. Now, instead of having 2 columns of 4 blocks, maybe have 4 columns of 2 blocks. And that's this picture. This is called a 4-way set associative cache. Your tag store now looks like this. You have only 2 indices, 0, 1. But now you have 4 possible things in your set. And data store also looks like this. This is the same picture. I just drew it in a different way so that I can accommodate the picture inside the same slide. But essentially, your logic to determine a hit becomes more difficult because now you have more comparators. And also, your mux becomes wider for the data store. So your latencies increase in this case also. And now your address looks a little bit different, right? Your index is only 1 bit now. And as you can see, you decide based on that bit which set you're accessing. And your tag has become larger, even larger, 4 bits. So clearly, likelihood of conflict misses are now even lower because you have more flexibility in the mapping. But now you have more tag comparators and a wider data mux and larger tags. Now, if you push it to the limit, you have a full associative cache. So basically, instead of having 2 columns, 4 columns of, let's go back over here. What I said over here as 2 columns of 4 blocks over here. Right? Now we have 4 columns of 2 blocks. How about having 8 columns of 1 block each? That's basically a fully associative cache. In this case, a block can be placed in any cache location. You eliminated the index bits. There are no more index bits. You're just comparing the tags. This is a fully associative cache. It's fully content addressable memory, if you will. You're comparing 5 bits. These comparators are larger. You have more comparators, 8 comparators over here. You have wider muxes. So clearly, this is longer latency, clearly, but you may be able to accommodate in your cycle time. It depends. But your conflict misses are even lower, and you have more potential to manage your cache. Now, basically, you have a decision. Whenever you want to evict some block, which one do you evict? You have a lot of flexibility. You can evict any of the blocks in the cache. And remember, we have 8 blocks. It's a small cache, but we have a lot of potential choices over here. So that's great from a management perspective, but not so great from a complexity perspective, as you can see. Okay, so basically, degree of associativity, what I introduced you is the associativity. How many blocks can be placed in a given set? You can also think of this as how many bits do you use to index the cache, right? Okay, degree of associativity is how many blocks can map to the same index or set. Higher associativity gives you higher hit rate. Downside is slower cache access time. Hit latency and data access latency both increase. And you have more expensive hardware, more comparators. Comparators become larger. And you get diminishing returns from higher associativity. So averaged across many workloads, this is kind of like an industry slide because I don't have the exact data over here. But as associativity increases, hit rate initially increases a lot, but over time, basically you get diminishing returns. But again, this is very much workload dependent. So this is just a general picture average across many, many workloads. Think of it that way, as opposed to a given number. So a workload may actually really benefit from 8-way associative, but it may not benefit from 1 to 4-way or 3, or anywhere between 1 to 8-way associative, right? Because you may actually have a conflicting pattern with 8 things involved. And once you're 8-way associative or higher, that's great. So it really depends on the workload access pattern. So there are issues in set associative caches. I'm going to finish very soon. But think of each block in a set having a priority, indicating how important it is to keep the block in the cache. The key issue is how do you determine and adjust block priorities to decide what to keep in the cache and what to evict from the cache? Because clearly you have, let's say you have a fully associative or set associative cache. You have all the blocks used in a set, and you have another incoming block that's different from what is inside the set already. Then the question is, how do you adjust the block priorities? Do you bring the incoming block into the cache by evicting something else, or do you keep the existing blocks in the cache? There are many design choices here, and there are 3 key design decisions in a set, basically. And these are called insertion, promotion, and eviction. Eviction is also a replacement, basically. So insertion is what happens to priorities whenever you're filling a block into the cache. How do you change those? Do you increase the priority of the thing that you're filling in? Do you reduce the priorities of things that are not used? So you can imagine many different policies. I'm not going to give you any policy at this point. We're going to look at some policies later in the next lecture. So where to insert the incoming block, whether or not to insert the block. These are all questions, basically. And what do you do to the other blocks? Promotion is what happens to priorities on a cache hit. Cache hit gives you more information also. So basically, cache fill is giving you some information. This block is not in the cache. What am I going to do to the set? Cache hit also gives you more information. I hit this block in the cache. I re-referenced it. So I have more information. What do I do to the priorities? Do you change the block priority? How do you change the block priority? Do you reduce the block priority of other blocks that are not accessed? So there are many design choices over here. And then finally, eviction and replacement. This is what happens to priorities on a cache miss, essentially. When you get a cache miss, which block do you evict? How do you adjust the priorities of different blocks that are in the cache at that point? So set associative caches enable a lot of decisions. In direct map caches, you have fewer decision space is smaller, basically, because you basically either evict the block that's in the cache or not evict it. That's the decision you need to make. Whereas here, if you are set associative, if you have many potential blocks mapping into the cache, and in existing cache, it could be 32-way or 64-way set associative. You may actually have 64 blocks mapping to the same index. In that case, you need to actually make a good decision if you want to manage your cache well. Okay, so eviction policy is which block in the set to replace on a cache miss. Very quickly, in any invalid block, first, I already mentioned this basically. If you have an invalid block, you should replace it. It doesn't make sense to replace a valid block if you already have an invalid block in the cache, right? Unless you have some other really, really good information about blocks. And if all are valid, you need to consult the replacement policy. This is also called an eviction policy, as I mentioned in the previous slide. And there are many replacement policies, and we're going to cover them in the next lecture. But just to prime your thinking, it could be random. You could decide randomly to pick which one. It could be first in, first out. It could be least recently used. It could be not most recently used. It could be least frequently used. And these require different information, actually, to keep. Random doesn't require any information to keep. You flip a coin. Well, maybe a random number generator, but it depends on how truly random you want to be in this particular case. But least recently used actually requires a priority ordering of the different blocks, as we will see in the next lecture. Not most recently used is easy. You just keep track of what's the most recently used block, right? So these differ in terms of the amount of information you need to keep about blocks in a cache, right? Least costly to refetch. Memory access may have different costs. We're going to talk about that in the next lecture. There may be hybrid replacement policies. Again, we're going to briefly talk about that in the next lecture because one replacement policy is not good for all patterns. Earlier, one of your fellow students mentioned maybe branch prediction ideas can be applied to caches. Yes, absolutely. This hybrid replacement policy is very similar to hybrid branch predictors. Different access patterns may benefit from different replacement policies, and you may actually have different replacement policies to cater for them. What is the optimal replacement policy? We're going to talk about that as well. Okay. And this is probably a great place to stop because after this, we're going to go into a little bit more detail into these management mechanisms, as well as other issues that arise in a memory hierarchy, in a modern memory hierarchy, in terms of how to manage the caches. Before I conclude, I should also say that there are some backup slides that have more examples on how do you index the cache. I gave you a toy example. I think actually it's enough, but these backup slides give you some more examples on a larger address, for example, in terms of how you address the cache, how you index the cache, what is the set associated with it, etc. So if you're interested in looking at those, they're already uploaded, and you can take a look at the backup slides. So I guess I will answer one question. There's a question saying, what makes a block invalid? So basically, the valid bit specifies whether the block is there or not. So what does it mean for a block to be invalid? That means that it didn't get fetched into the cache when you were querying the cache. That's what it means semantically, right? And initially, when you start out your system, all of the blocks in a cache are invalid, right? Because you didn't fetch anything into the cache. And this is designated by the valid bits in the cache. So hopefully this is clear. You have to have a valid bit because you have to distinguish whether the data that's stored randomly in that particular location is something that you loaded into the cache willingly or something that was there, that happened to be there, right? So the valid bit, no, it's not only for system startup. That's also a very good question. There's a question that asked, is it only for system startup? The answer is no, because you may actually decide to invalidate a block for other reasons. And this becomes more complicated, but well, what could the other reasons be? In a multiprocessor, two different processors may be caching the same location, and one processor may write to the location, which makes the other processor's cache stale, which means that when this other processor is writing to its own cache, it should invalidate the other cache. That's one way of designing cache coherency. So yes, usually valid bits are also needed for the cache coherency protocol. In fact, cache coherency protocols, modern cache coherency protocols require even more bits than the valid bits. They require more like 2 or 3 or 4 bits in existing cache coherency protocols. So that's a very good question. But you may also decide to invalidate it because you're not going to use the cache block and you want to make it available for replacement, for placement for other blocks, right? There could be other reasons to invalidate it. Okay, these are very good questions. And I think if there are no more questions, we should stop at this point. Tomorrow, we're going to pick up where we left, and we're going to go more into caching, hopefully cover some really interesting topics. And then we're going to start virtual memory if time permits. Otherwise, we're going to start virtual memory next week. Okay, take care, and I will see you tomorrow.